In the last lecture, we saw how we could reduce the sample rate of a digital signal by downsampling or using proper decimation. And we also saw how we could increase the rate of a signal by upsampling or interpolation to fill in the missing samples. So we concatenate a downsampling operation by an upsampling operation of the same factor will arrive back at a signal of the same rate that we had in the beginning that we input to the system. So if we build this explicit system that was shown in the previous picture, so we have a proper decimation circuit followed by a proper interpolation circuit. Then what can we say about the relation between x of n and y of n in terms of the discrete time Fourier transform? So can we say that the discrete time Fourier transform of the output sequence y of n is equal to the discrete time Fourier transform of the input sequence x of n for all frequencies? Or can we say that the discrete time Fourier transform for the output is equal to the discrete time Fourier transform for the input, but only for frequencies up to 1/4, after which the output discrete time Fourier transform is identically equal to 0? Or can we say that the output discrete time Fourier transform is equal to the input for these same frequencies, but the output discrete time Fourier transform is equal to time or frequency shifted version of the input discrete time Fourier transform? Well, the correct answer is option number 2. So if we built this system, the discrete time Fourier transform of the output would be equal to the discrete time Fourier transform of the input, but only for frequencies up to 1/4. And we'll see that later on in an example. So let's consider that example. Let's consider the system that we looked at so far. So we have a proper decimation followed by a proper interpolation in order to recover the original data rate of the signal. So let's first look at the operation that the decimator is performing. So the system from x of n to v0 of m in this case, in terms of the discrete time Fourier transform. So interpreting the formula again for the decimation, we see that what we get is a frequency scaled and shifted version of the original signal in the first term, given here. But since we applied the low-pass filter, we will not observe all of these frequencies in that part of the equation. So this low-pass filter will remove frequencies in a range, like this. Then we have a second part to the equation, which is this frequency shifted version, which will fill in the blanks. So if we include that, we get this part, and adding them up as before gives us the complete discrete time Fourier transform for the sequence or signal v0 of m, which has half the rate of the previous one. And we can compare that to the original spectrum, and we see that v0 of nu here is a representation of the original spectrum of the original discrete time Fourier transform for the range -1/4 to 1/4, and that is represented in the frequency range -1/2 to 1/2 in the downsampled signal. So let's consider now what happens when we do interpolation with this system. So we start with the signal v0 that we just obtained, and we want to create the signal y of n in terms of its discrete time Fourier transform. So what is prescribed for the upsampler is simply a stretching in or compacting in frequency of the original signal v0 of m. So if we look at that, this is what we get. But then that is followed by a low-pass filter which removes the high frequency components. And if you remember, in the upsampler or the interpolator, we didn't just have a low-pass filter, but we also had a gain of 2, which doubles the amplitude of the output signal. And this gives us the following signal. So the following signal is simply the frequency range of v0 of nu squeezed together into the range of -1/4 to 1/4 and also corrected in amplitude. So if we now compare this to the original spectrum, we can look at the discrete time Fourier transform of the input signal and the output signal, and what we see is that the discrete time Fourier transform of the output signal is nothing else than a low-pass filtered version of the discrete time Fourier transform of the input signal, or rather to say that the output signal is a low-pass filtered or ideally low-pass filtered version of the input signal x of n here. And here we also see the reason for including this factor 2 in the interpolation circuit in order to recover the gain that we had in the discrete time Fourier transform from the input. So we get exactly equal discrete time Fourier transforms for the range -1,4 to 1,4. However, in the reconstructed version here, we lose the high frequencies. And this is a consequence of the fact that we move by a lower rate system. So this lower rate signal cannot carry all the information in the original signal x of n. So when we reconstruct, there will inevitably be some form of loss. And we've decided to construct this system in such a way that what we lose is exactly these high frequency components. So one can ask, what would happen if we replace now these low-pass filters that we used in the downsampling and the interpolation by instead using high-pass filters? So these would be filters which in the first case would remove all frequencies within this range -1,4 to 1/4 and keep the high frequency range instead. And then the interpolator filter would still include the gain, but it would keep higher frequencies. So we can answer that question by doing the same exercise over again. So we start with the original input spectrum. We look at this term, which just amounts to a frequency scaled version of the input, and we apply the filter that we had here in the circuit. And what this does now, since it's a high-pass filter, it will no longer keep the low-pass component, but it will keep the high-pass component as such. However, we see by the construction of this high-pass filter, we still create these gaps in the spectrum, which are then filled by the frequency shifted version of the signal, like such. So when we add everything up, this is what we get. So essentially what we have in this range from -1/2 to 1/2 is no longer a representation of the frequencies between -1,4 and 1,4, but instead representation of frequencies in the higher frequency range, even though the frequencies within this range do not correspond directly to these, but they correspond to a mirrored version of these higher frequencies. And you can see that it's this part of the spectrum which ends up here, and it's this part of the spectrum which ends up here, also scaled in both in amplitude and in terms of frequency. So let's look at what happens when we reconstruct this. So when we go from V1 to Y of n. So we start with V1 of n, or the discrete time Fourier transform of the signal V1 of m. And as prescribed by the upsampler, we do a frequency compacting. So all the frequencies between -1/2 and 1/2 get squeezed into the frequencies -1/4 to 1/4. And of course we have the repetitive structure of the discrete time Fourier transform due to the periodicity of the discrete time Fourier transform for V1 of m. So that is the upsampling part, but then comes the filter, which in this case is a high-pass filter, so it would keep the higher frequency components and it would null out the lower frequency components, and it would give us this. And you also note the gain here of 2 in this low-pass filter, doubling the amplitude of the output. So now we can compare the spectrum of the full spectrum of the signal V1 of m, which gets mapped back into a spectrum for Y of n, but through a mirroring operation, which places this part here with double amplitude and this part here with double amplitude. But this mirroring of the spectrum is exactly what happened in the first part. So overall, if we compare the full system now with the input discrete time Fourier transform and the output discrete time Fourier transform, the whole system just acts as a high-pass filter. So it removes frequencies in the range -1/4 to 1/4, but it keeps frequencies in the range -1/2 to -1/4 and 1/4 to 1/2. So this part of the spectrum. So what we can do now is we can take these two systems that we just studied, and we could join them in parallel. So we have the first system, we have the second system. So the first system delivers low frequency components, the second system delivers high frequency components, and if we add them together, what we will get is a perfect reconstruction of what we had at the input. So one can ask what the reason for doing this is, right? So we have a complicated system, and all it does is to recover the original signal x of n and y of n. And the interesting part about this system is we have these two intermediate systems, or two intermediate signals, V0 and V1, where V0 carries only low frequency components and V1 only carries high frequency component. And this is a basis of many compression schemes where we may wish to compress low frequency signals and high frequency signals differently using some models in order to get good compression for data storage. So let's consider a question related to this. So suppose that we have a discrete time signal x of n, which is a sampled signal at fs samples per second. Then how many samples per second would we have combined in v0 and v1? Would we have fs over 2 samples per second in these two signals combined? Would we have fs samples per second? Or would we have 2 fs samples per second? The correct answer is that we would have fs samples per second, the same as in the signal x of n. And the way to see this is that in the first branch we have a downsampling by a factor of 2, which halves the number of samples per second. So in v0 alone we would have fs over 2 samples per second. But we will also have fs over 2 samples per second in v1. So combining this yields an overall number of samples per second according to fs, or equal to fs. So what we see is that we're able to split the signal x of n into two frequency components, v0 and v1, without increasing the sample rate of the original signal. And this is a useful part for compression. So we've seen that a filter bank can be used to split a signal into two frequency components, or two spectral bands. But we could also use them to split a signal into several more filter banks. So one easy way of doing that is to simply insert a filter bank into a filter bank. So we first split the signal into two frequency bands, and then we pick one of those frequency bands and further split it. And as noted, this is one of the basic components in many compression schemes. So you begin with taking your original signal that you want to compress and store, and you split it into several different frequency bands, or signals containing the information in several different frequency bands of the original signal. And then you individually compress and quantize these in order to store them efficiently. And then you can base the different quantization on how subjectively sensitive you are to quantization effects in each on the individual frequency of the original audio spectrum, and that will lead to very efficient compression schemes, like for instance MP3 or AAC. So what we would get if you look at this system, so in this case we do split the signal into two frequency bands, and then we split the lower frequency band into two separate frequency bands. We could get representations of the three different frequency bands contained in the original signal x of n in the signal v00, v01, and v1 as follows. Now the only problem with this from a practical point of view is that so far we've assumed ideal filters for H0, H00, H01, and so on. And as we know, we cannot exactly implement ideal filters. So what we could try to do is we could try to approximate ideal filters as well as we can given our complexity constraints. But it turns out that we can actually tolerate imperfect filters in many of these filter bank systems and still achieve perfect reconstruction. And the way to do that is to ensure that the filters are selected in such a way that once you add up the signals now containing the aliasing effect, the aliasing exactly cancels at these points of addition. If we apply the formulas we have for downsampling and upsampling, decimation and interpolation, we can derive a formula for the C transform of the output in terms of the C transform of the input and these now non-ideal filters in case of a two-branch filter bank, and it would look like this. So if in this formula we would have x of z, which is the C transform of the input sequence, and we would also have a term related to x of minus z, and this term is what would be the aliasing remaining in the output signal. So if we choose our filters such that this term here becomes identically equal to 0, this term would vanish and we would only have this term. And if we at the same time choose our filters so that this amounts to a constant 2, which would counteract this 1 over half which we have, or 1 over 2 which we have here, we would obtain a formula which said that y of z is equal to x of z, the input sequence, meaning perfect reconstruction. So that gives us two conditions, so this condition and this condition, which together guarantee perfect reconstruction by a two-branch filter bank, even if the filters themselves are non-ideal. The problem with this is that it's very hard to satisfy these two simultaneously if we wish to have filters which are causal at the same time. However, what we could do is we could relax this assumption that this should work out to be a constant and instead let it be said to the minus L, where L is a constant, and that would correspond to a constant time delay. So using this condition instead, we could get that the output sequence is simply a slightly time delayed version of the input, and that is pretty much as good as perfect reconstruction. And we can also derive sufficient condition for this aliasing reduction criteria in terms of just pairs of filters. So we can choose the reconstructing filters based on the high pass filter and the low pass filter that is used at the input in order to achieve the second condition. So these conditions are quite often used in practice in order to design or find filters that satisfy these two conditions. So what does it mean to insert sign changes in the Z variable in the Z transform? So suppose that we have an FIR filter with an impulse response given by 1, 2, 3, 4, 5, where the 0th order lag is for this one component. What would then G of n be if G of n is related to H of n through this Z transform expression? So would G of n simply be a time-shifted version of H of n, where the 0th order lag would end up with the last sample? Or would it instead be a time-flipped version, where it starts with the component -5 and then goes down to 1? Or would this imply that we have a sign change of every second component in G of n as related to H of n, but having the 0th order term at the same place? Well, correct answer is option number 3, and this can be seen by writing out the Z transform explicitly and putting in the minus. So in the Z transform, the minus would cancel in all even terms, but it would remain in all odd terms, and this is what causes the sign change for all odd ordered components in G of n. So to summarize, Filterbanks can be used to split a signal into frequency components, and this is very useful for signal analysis and also for compression methods, and it's the basis of many popular compression methods like MP3 and AAC. So perfect reconstruction can also be achieved without having to use ideal filters, but in that case there will be some aliasing in the downsample part, and in the reconstruction part we have to cancel that somehow, and this leads to a number of conditions that has to be satisfied for the filters involved in order to achieve this perfect reconstruction.